Bismillahirrahmanirrahim. Welcome to Pakistan International School Taib. This is Fayaz Al-Ansari, Professor of Chemistry. Now students, we are talking about the grade 12, chapter number 14, and yesterday we started D block and F block elements. So now continue this topic and we are going to discuss today binding energy. Binding energy. So if you see the page number 62, grade 12, chapter number 14, transition elements, binding energies. So you know metals are very hard and heavy. They are rigid, hard and heavy. So when we say metals are hard and heavy, it means they have very strong binding energies. In order to understand the mechanical properties of transition elements, already I told you, means hardness, flexibility. So they have very high binding energy, strong forces, tough, malleable and ductile. Malleability and ductility of the metal means they change into sheets and wires. When you press, when you going to apply the pressure, so they will not fracture. So instead of fracturing, they change into sheets and wires. But if you are going to press this plastic, if you press the glass, if you press the carbon, sulfur, they are going to be fractured. They change into small pieces, powder, but metals do not. This is a very important property and we use in our daily life. Malleable and ductile. Toughness of metal, I told you, due to the greater binding energies, is strong force between the metal atoms. But these binding energies are not same for all the metals. There is going to be change. So written here, variation in the binding energies. When we move from left to right in the periodic table in D blocks, the number of electron increases up to 5B group. Means one should have 1 in the D, 2 electrons in D, 3 electrons in D, 4 electrons in D, like this one. So number of electron in D is going to be increased up to 5 group, means vanadium. If you see the graph, figure number 14.2, binding energies are going to be increased. Don't see for potassium and calcium. Potassium is an alkali metal and calcium is an alkaline earth metal. So starting from scandium. Scandium, titanium, vanadium is a maximum. 6 group family, vanadium is a maximum, then decreasing chromium, highly decreased to manganese, then increased to iron, cobalt, nickel, then decreased to copper, and finally bottom to the zinc. The reason because why they have the high binding energies, greater binding energies, the reason given here because of s electrons of the outermost shell take part in the chemical bonding along with the half-filled d orbitals. S electrons and partially filled, half-filled d orbitals participating in the bonding formation. That is why the D series elements, metals, have greater binding energies. So this is given in the 14.2 graph. I told you up to group number 5B, vanadium maximum, then manganese is going to be decreased. If you see, chromium and manganese decreases. After that, the pairing of electrons start. non-pairing. If you draw the electronic configuration, you will see the pairing of electrons, non-pairing of electrons. So when the pairing of electrons are going to be more, the unpaired electrons become 0 at a group number 2b, means zinc. That's why zinc has a very weak binding energy. It means that binding energies forces go on increasing up to the vanadium very high, then chromium decreasing and manganese very low, and then iron, Fe, iron, cobalt, nickel, zinc, bottom. This is one thing. Second thing is that in the 5D series, cesium is a group number 1 element, barium is a group number 2 element starting from lanthanum, then hafnium, then tellurium, then tungsten top. Tungsten has a highest binding energy, top. Then it is going to be decreased up to the mercury because it has a paired electron, same as for the zinc. So mercury is a metal, but it is in liquid form. It is in the liquid state. So binding energies are very weak in the mercury you are seeing in the graph. So this is about the binding energies and reason I told you, and variation in binding energies in the different groups in the D series already I told you. There is one thing very important for the transition metals. Transition metals, they have variable valence. Variable valence number, variable oxidation state, variable oxidation state. Just like copper positive 1, copper positive 2, iron positive 2 and iron positive 3, etc. So they have variable. Why the transition metals have variable oxidation state? It's no doubt that transition metals are highly positive character. They are electropositive in nature, have positive oxidation states. All 3D series elements show oxidation state of 2 in addition of higher oxidation states when the electrons of 4s orbital taking part in the binding. Why these elements show variable oxidation states? Because they have d electrons in addition of s electron for the purpose of bond formation. Already we discussed in the previous topic. When they are going to form a bond, so in the bond formation, d electrons involved and s electrons involved in the bond formation. That is why they show variable oxidation states. The elements having several n-1 d and ns electron, the energy of n-1 d and s orbitals are very close together. So that's why the d and -1 d electrons are easily lost in as n s electrons. So in the highest oxidation state of first 5 elements, s and d electrons are used for the bonding purpose. So among the 3D series, if you see the unpaired electron in manganese, unpaired electrons are 1, 2, 3, 4, 5. Unpaired. More unpaired electron, highest the oxidation state. So manganese 1, 2, 3, 4, 5, 6 and 7 oxidation states for the manganese. So if you see scandium, it has only one unpaired electron, shows only 2 oxidation states, 2 and 3. titanium 1, 2, 2, 3, 4, vanadium 1, 2, 3, 2, 3, 4, 5, chromium 1, 2, 3, 4, 2, 3, 4, 5, 6 like this one. Zinc has no unpaired electrons, so it always shows positive 2 oxidation state. Zinc shows always, never change. Zinc sulfate, zinc chloride, zinc nitrate. These are the compounds in which zinc has a positive 2 oxidation states because of absence of the unpaired electrons. D, 3D is filled with the 10, 4s is filled with the 2. Due to this reason, dear students, this is about the variable oxidation states of the D series. There is another very important property of the D series. They have a catalytic activity. They use in the catalyst. Catalyst is a substance maybe in the pure element form or in the compound form. Mostly in the catalyst, either in the elemental form or in a compound form, transition matters involved. Transition matters involved. So catalyst is a substance which speed up the chemical reaction, fast the chemical reaction, not start. Catalyst does not start the chemical reaction. Chemical reaction is already started, but it is a slower one. There are many others also. We use also negative catalyst. If the chemical reaction is very fast, we can decrease its rate of chemical reaction to using the negative catalyst. Okay. So catalyst is a substance which speed up the chemical reaction and without any participating in the chemical reaction, does not participate. After completion of the chemical reaction, we can recover the catalyst in the same, but the phase may be changed. So students, catalyst very important. Vanadium pentoxide, chromium is going to be used, iron is going to be used, iron oxide is going to be used, manganese dioxide is going to be used, many catalysts you will see. So these are going to be used to increase the speed of the chemical reaction. Very small amount of catalyst is used in this purpose. So examples are given in industrial means we are going to prepare methanol, methyl alcohol in industry. Zinc oxide and chromium oxide used as a catalyst. Zinc is a transition metal and chromium is also transition metal. Nickel, platinum, palladium used for the hydrogenation, for hardening the oil. Oil is going to change into ghee or oil change into margarine. Unsaturated compounds can be changed into saturated one by using hydrogen. The process is called hydrogenation and catalysts are used. For the preparation of nitric acid in Ostwald process, so the platinum is going to be used for this purpose. Manganese dioxide is used for preparation of oxygen from the potassium chlorate in the laboratory. When you are going to prepare oxygen gas in the laboratory by the decomposition of potassium chlorate, you have to mix the manganese dioxide black powder. Also, Manganese dioxide, we use a catalyst for decomposition of hydrogen peroxide. Titanium chloride is used catalyst for the manufacture of plastic, and good quality plastics can be manufactured. Vanadium pentoxide is going to be used for the oxidation of sulfur dioxide to give sulfur trioxide for the manufacture of sulfuric acid on contact process. Iron is used as a catalyst for synthesis of ammonia on the Haber process. 1% sodium oxide, potassium oxide, they are not transition metals. 1% silicon oxide, aluminum oxide, not transition metals. They use as a promoters. Promoters are called catalysts for the catalyst. Students, this is a very important, specific, particular catalyst is used for the particular chemical reaction. So that is why when you use a specific catalyst for a specific chemical reaction, if the chemical reaction is slow, then you have to use promoter to increase further activity of the catalyst. So these are called promoters. So dear student, this is about the catalytic activity of the D block element. Magnetic behavior. Magnetic behavior, you know, mostly the metals, they attract towards magnet. This is the magnetic property of the metals. And why these metals attract towards magnetic, these elements are called paramagnetic. This behavior is called paramagnetic behavior of the transition metals. They attract towards magnetic field. The compounds and transition elements which attract towards magnetic field are called paramagnetic. How this process, paramagnetism, is due to the unpaired electrons, unpaired with the same spin lines. You learn in the grade 11 paramagnetic nature of oxygen molecule due to presence of unpaired electron in the antibonding to be Y star and to be Z star in the same spin. Due to the presence of unpaired electrons in the metal or in their compounds is a paramagnetism. The substances which can magnetize are called ferromagnetic. They are magnetized, changing magnet. Iron, cobalt, nickel are the ferromagnetic. And other one is called diamagnetic. They are called diamagnetic. So these diamagnetic is due to the paired electrons, and these elements and their compounds are weakly repelled to the magnetic field. No attraction, repulsion is there. So slightly repelled by magnetic field. And this magnetic movement is related to the number of unpaired electron n by this equation. So this is the magneton mu. We call it mu, magneton, under root n -2. So this is the formula you have to use for the magnetism. So it is called a Bohr magneton, BM, Bohr magneton. By measuring the magnetic movement, the nature of transition metals, compounds and the oxidation state of the transition metals can be calculated by using this formula. So dear students, this is called magnetic behavior. Then very other important property of transition metal is alloy formation. You know the many types of alloys: stainless steel, brass, bronze, nichrome, gunmetal, many types. There are many types. So, dear students, alloy is a very common we prepare from the iron by mixing with other metals. The reason because iron gets rust very quickly. So different kinds of ornaments, different kinds of other materials are prepared or made in industries by mixing other metals or elements with the iron. Alloy is a mixture of two or more than two metals. Transition metals form alloy with each other, I told you. Reason: because the transition metals mostly they have similar properties, similar sizes, atomic size is mostly similar, they are easily to be the up position in the crystal lattice. They form substitutional alloy. What is the substitution alloy? Because other elements substitute the iron. One element is they substitute among themselves. Alloy of steels are very common. Iron, I told you, substituted by chromium, manganese, nickel. There are thousands types of steel, many kinds. By using different proportions are going to be used. That is why brass, bronze and coinage alloys are best alloys. So dear students, this topic may become in the short question, may become in the MCQs. Maybe he asked about the proportion, composition of brass, copper 60 to 80%, zinc 20 to 40%. Brass, strong alloy. Copper is soft and flexible, does not corrode, low melting point, easy to use, make locks, water traps, pipes, artificial jewelry, door handles, part of machines. Bronze, 90 to 95% copper, 5 to 10% tin, strong, brilliant, long lasting, does not corrode, prepare medals, coins, badges, bullets. Beside these decorative articles also made from the alloy. Nichrome, nickel 60%, chromium 15%, iron 25%, used in the electric heaters, flames of furnaces. Alloys are prepared according to requirement and their characteristics and demand. They are comparatively cheap, strong, flexible alloy and hard can be prepared. They have long life because does not corrode. They are durable, high melting points. They are better conductor, but non-conductors alloy are also prepared. So dear students, quick quizzes. Do these yourself. Must do these questions from the exercises and also from these quick quizzes may become an examination. So dear students, here we finished, and the next lecture is a very important, and many questions asked from this topic, and I'm going to leave this topic. Is called coordination compounds. So inshallah, in the next lecture we will discuss the coordination compounds. These are very important. So my suggestion is that you have to work hard daily basis, because your result is based upon grade 12, and grade 12 is more difficult than grade 11. Very lengthy syllabus and very difficult chapters, very long and difficult chapters. So you have the hard work. So this is, now we end today. Thank you.